All right. So yeah, so I want to talk about plans for Sedil 2 and Sedil 1. Our current Sedil, uh, Sedil 1 point, whatever we have left it on there, uh, is we needs a new sort of like a new architecture for the compiler. We weren't even really thinking of it as a compiler, and consequently, it's the way it's set up now. It's just kind of hard to get in and modify, and so we need. And I think that could be challenging. In fact, Garrett Morris, who's joined the faculty here this past semester, um, has some pretty cool ideas about how to make more extensible, flexible compilers. So we might get his advice on this. But we need, we want Sedil to be kind of more like GHC, where you can where you can get in and hopefully with some help from somebody manage to add new features, new ideas, and because a lot of us are testing out ideas, and we can sort of test them out at sort of the language level we've implemented, but what we have today. But we'd like to actually sort of incorporate those into the language and sort of get a nicer way to express these ideas. So the tool needs a new architecture, but also we can improve the theory, and that's what I want to focus on today. And in particular, the sort of target here, we can improve in two ways, actually in several ways. We can actually achieve a smaller core theory, a smaller core type theory, which I'll explain a little bit what I'm talking about there. We also have the possibility could be more flexible about the kind of logic that it's based on. In particular, the architecture I'm going to try to explain here in the next half hour would allow us to use classical reasoning without requiring, I've posted on my blog sometimes about, I have some objections to using like what do we call it? Computational classical type theory, where you basically have sort of like a Curry-Howard isomorphism with classical logic, and you program with that. And there's just some stuff that I personally think is worrisome about this. I mean, you basically get to do things like, it looks like you're writing programs that case split on oracles. And there's a computational interpretation of that, but it's not what you expect. It doesn't actually magically figure out whether a Turing machine halts or not, and then lets you take the appropriate action. So anyway, the architecture I want to tell you about would allow us to use classical logic without sort of polluting the programming language with it if we didn't want to. But on the same token, it doesn't require classical logic. It's just sort of saying, like, we could pick a different logic if we wanted to. And the final thing, and sort of when all this adds up, I've been sort of kicking these ideas around. When all these start to add up, it's like, this sounds like a good idea. This is worth the investment, even if it takes a while. We could we could support an extensional equality type, which is a pretty desirable thing. And so I have to say some things about all these points. This last one, though, if you're not familiar with what this is talking about, like right now in Sedil, it could happen, in Sedil 1, you can have functions like f and g, where, like, let's say for all inputs, for all x of type A, fx equals gx, but f doesn't equal g. And so, a good examples of sort of non-extensionality, and you have this stuff in Coq and Agda are the same in this regard, but unless you sort of throw in some postulate that says things are extensional. Now, I don't know about part of homotopy type theory is to try to give you some more extensional properties. So some of you guys might know better than me what the status of that is, whether cubical Agda or something gives you a similar extensional property. I actually do not know, but like in not counting that particular theory where I'm not confident what the situation is, but in in Conquer-Agda or Cedille-1, you can't prove that merge sort equals quicksort or something like that, or merge sort equals insertion sort. You cannot prove those are equal, even though they have the same behavior, right? They take the same input list to the same output lists. And so in some cases, so when we're doing sort of higher order stuff, it would be nice, and a lot of type theorists out there have thought this would be very desirable, and we agree. It'd be nice to be able to get this kind of extensional equality, that I could actually prove the functions are equal. Now, then the notion of equality you use, like, what does it mean to be equal? You know, in Cedille right now, equality means they're beta eta equal. And yes, you know, definitely if you have merge sort and quicksort are not beta eta equal pieces of code. Like if you just look at the lambda terms and compare them, they're different. The algorithms work differently, even though they give you the same extensional, like input output behavior. So anyway, so it would be, for a lot of situations, it actually would be pretty cool to be able to say that they're actually equal based on their behavior. I mean, yeah, at the same token, there's sometimes where you might not want things to be equal. Right? I mean, there's actually the rich design space, because you might not want to equate, say, insertion sort and merge sort, since insertion sort has a different asymptotic running time than merge sort. You might actually like to be able to distinguish those in your theory. So that would be cool too. And I've thought about that a little bit as well. But for now, you know, the focus today, for at least in what I've been thinking about, is like how to get this extensional equality, and even more intentional equality, which seems like an opposite goal. I'm not addressing that right here. So anyway, so how do we do, what is the proposal for how to do these amazing things? Well, so here's the proposed architecture. So we start with our surface language, and this is true. Actually, I'll see if I can sort of compare Cedille-1 and proposed Cedille-2 setup. So in both of them, we've got some surface language. And in fact, you know, part of our research goal and mission is to explore cool new surface language features, like basically just nicer, more, you know, powerful, flexible ways to write, you know, richly typed programs and verify properties about them. We want to explore that, but actually similar to the situation with Haskell. In Haskell, they you know, explore all kinds of crazy different extensions and typing features and things. But my understanding is that at the end, everything has to make it down to their core type theory. So you have some, you know, source file here, you know, your foo.ced, and it gets translated down. This is what Cedille-1 does right now. It gets translated down to, well, something that we can just give a different suffix to if we care to, but basically our core type theory. And here for Cedille-1, the core type theory is this, you know, CD, calculus of dependent lambda eliminations, simplified version, where we basically have Curry style calculus of constructions plus quality type. I mean, this is, if you've studied about Cedille so far, you're familiar with this. Dependent intersection type and implicit products. Okay, so we're pretty happy with this as a core. We have been pretty happy with this as a core theory. I mean, it's small. We have proved on paper, you know, the properties that we want to prove about it. It's definitely an original combination of these different ingredients, but it's not, I mean, the Curry style CC part, like you could say that's like pretty textbook, and then we add these somewhat other weird features, but it seems pretty benign, you know. So like sort of like if you compare this kind of like status of core theory, you know, like, it's something that people might find a little peculiar, but it's, you know, it's sort of like, you know, it's verified, at least on paper, and it's quite small. Our checker for it now that we've used for a while, for the Con wrote, is less than 1,000 lines of Haskell, and it's, you know, it's sufficient for our service language needs. So everything we've wanted to do from our service language, we've been able to translate down. And in fact, what we usually do, as you know, who are doing this, we figure out how to do something at the essentially the core type theory level, and then we're going to try to figure out how to make a nicer surface language, version of it. Okay, so that's kind of the Cedille 1 picture. Now, so the Cedille 2 picture, oh, okay, so I should say, over here, if you have something like, say you have something like add, like, nat to nat to nat or something, then in the end, what you translate this down to, actually, I'd kind of have to check to make sure I know what we actually do at the moment. But I believe that in the end, you actually do get a version of add that is this kind of nat to nat function, nat to nat to nat function. But of course, one of the main pieces of technology we use is that the data types, we use these lambda encodings to eliminate the data types. And so you have this thing where nat is this dependent intersection of, and then it sort of depends on exactly how we've decided to do that. But one perfectly sensible way is to say a nat is an X of type top, where top types everything, even non-terminating terms, whatever crazy stuff. It's just some term that satisfies, effectively that satisfies induction for X. Okay, and let's see, yeah. I think I might break out and say just a tiny bit more about that, because a big piece of this translation is based on realizability semantics for types. Semantics for types. So I want to remind you or tell you a little bit about that to contrast with a different semantics for types that I'm proposing we would use for Cedille 2. So, okay, so for this semantics for types, if we have in our service language, again, let's say like add nat to nat to nat, I'm not saying this is exactly what actually ends up happening now, but the kind of semantics that we're talking about is where we think of this sort of typing property. So sort of like add realizes, like we get a little property out that says that I'm going to just write for alls, not really caring whether there are actual erased implicit products of Cedille or not. I just want to indicate the sort of logical structure here that says like for all X, just any old X. Now we're going to turn, basically we're going to turn types into unary predicates. So we start up here with a type, and we're going to turn it into a top to type. Actually, so sorry, let me say, I can at least write a star, which is fine for type. So we take something of kind star, and we're actually going to turn it into something of kind top arrow star. So the predicate, let's see, yeah. So when we have a type like this, we're going to turn that into a property that add should satisfy, and we're going to manage to get a proof that add really does satisfy that property. And the property is, if you take for any old X out there, if you know that this X is a nat, again, imagine, like I didn't say how to do that part of the translation, but imagine that we somehow have managed to translate every type is getting turned into a predicate. In other words, bool is getting turned into a predicate that's trying to make a statement about a Boolean, let's say. So imagine that we've done that somehow, sort of by induction in this little example, that we've done that for nat. So then add realizes is going to say, well, for every X, if X is a nat, and for every Y, if Y is a nat, then add XY is also a nat. Okay, so we've kind of this. This is obviously a bit of necessity for time and my lack of complete formalized grasp of this. It's a little sketchy, but we're basically turning types into properties, and so the NAT type turns into this property that says you are a NAT. This piece of code, you're a NAT, and essentially boiling down to you behave like a NAT. And so that having a typing like add having this type in your service language translates down into this statement that given two things that behave like NATs, add of those two things also behaves like a NAT. And so this kind of realizability factors into our is an important part of how we do our translation down in CDEAL 1. And okay, so and I wanted to say this because and now I think I need to move my CDEAL 2 column over a little bit. Because in CDEAL 2, my proposal is to use a different semantics, not this realizability semantics, but well, in fact, what's funny is we're basically going to generalize from unary predicates to binary predicates, which doesn't seem like it doesn't seem like that. This seems so profound. Although Chris can tell you, and I can tell you, assure you, having tried wading through some of the examples, on the downside, it does seem to generate, I mean, things get hairier when all of a sudden everything is a binary predicate instead of a unary predicate. So that's a potential negative of this proposal. But anyway, let's see, let's go back to what we say here. Oh yeah, so now here, it's the same picture, the same sort of general setup. We're gonna start from service language, translate down to a core language. But what we're gonna do is, first we're gonna be more explicit about actually taking a piece of code like add in our service language and translating it. So add, which has this type, to repeat myself here, and translating it down explicitly into kind of two pieces, an untyped function. So an add of type top, that's just this like lambda. It could be, you know, depending on how you've written this or whatever. It's just the church encoded lambda add function. It doesn't matter what that code is now for purposes of understanding what I'm saying. We just translate it down to this untyped program, and then we're going to translate it down, and then the other part of the translation is going to translate this into a proof, you know, sort of add, you know, well, this is going to be add parametricity, that's going to state this property that, you know, so the semantics for the types is turning types into properties. And so whatever typing you had originally, you're going to turn it down into a proof of the property that you're interpreting the type as. So here you would turn this into, whoops, a proof about add. So similar to this add realizes one that I just showed, but here now we're going to do essentially, you could think of it as binary realizability, but I don't think anybody says that. They talk about parametricity, but funnily enough, unless I'm really missing something, that just seems one way to look at that is just as a generalization of realizability to higher arity relations. So, you know, so what that is going to look like is it's going to say, so I'm writing it this way. Again, it's sort of sketchy, but I hope you can see some interesting points here. And in comparison with the sort of unary realizability version. So now we're going to say for any two, so now we're going to interpret types as binary predicates on two terms. And so we're supposed to express a relationship that those two terms behave the same way according to the typing interface. Okay, so I'm actually like totally in love with this idea at some profound computer science level. You know, we all know about like, oh yeah, computer science is all about abstraction. And if you've, taught or explained this sort of thing, you explain to people like, well, things that are different in some ways, we could view them at a certain level of abstraction, they'd be the same. Like when I'm teaching in class, we're like, we have a room full of students and each one of us is a very particular individual. But if we abstract and we just say, let's just count how many human beings are in the room, then we've sort of identified everybody by throwing away a bunch of their, just, viewing them temporarily or whatever, throwing away a bunch of details. So we've equated everybody. That's another way to express abstractions, to say we consider these things to be the same for purposes of our abstraction. And yet, so that seems like a really basic idea in computer science, and yet it doesn't make its way into any kind of type theory that I know of exactly. And so this actually is sort of trying to do that. It's sort of trying to be a theory about equating things up to some interface. I mean, that's the idea of parametricity, and I'm just sort of proposing to try to incorporate that into Cedil. And so, the way this would look, we say, like, well, if you have two terms now, because these are, now everything's a binary predicate, which does make it a bit hairier, which could be bad, I don't know. And you're basically going to say, well, when we say nat x prime, now what we should think of that this is expressing is that x and x prime behave the same way if you treat them as nats. Like if you use the nat interface, then you wouldn't be able to tell the difference between x and x prime. Okay, so they're equal. This is an extensional notion of equality. Already, like just taking the just moving from unary, like realizability, unary parametricity or realizability, to binary parametricity, all of a sudden your definition of the type, the core idea of your type, is a form of extensional equality. You say they're going to behave the same way up to this natural number interface. So you say, all right, if you have, so we have pairs of inputs, so same kind of thing here. If you have y and y prime that you can't distinguish, if you agree to treat them as nats, then in the end, you wouldn't be able to distinguish add x y from add x prime y prime. Okay, so 2 points here. One, we've separated, we've turned, and we maybe could have done some of this in Cedil 1. I didn't really think about how much this particular idea could have been played out in Cedil 1. We've turned our sort of surface language typing, surface language T of type A, let's say, into an untyped T with proof that it satisfies the property that the semantics tells you this is what A is really trying to say. It's really trying, but this is one, it's really trying to say it preserves, this, it maps equal inputs to equal outputs, or equivalent inputs to equivalent outputs, with proof of this sort of parametricity property of T. So this is kind of, again, we probably maybe could have done something like this for Cedil 1, but it's saying, see, you might have missed in all my verbiage here that this core language doesn't need dependent types at all, really. It doesn't need dependent types. We just have programs and proofs about their behavior. That seems really simple. And so kind of looking in reverse, this idea is sort of saying, when you see dependent types and everybody's like, socks are on fire over this idea and how amazing it would be for programming, what you're really saying, though, is it's just a convenient way of writing a program and a proof about the program kind of at the same time. And this semantics is saying, that was great. We love that. Let's do that. But it's not necessary. Kind of when you're just translating down, you could just translate to a core language where you don't try to do that. You just say program, proof about the program. And that's where this kind of thing I was saying about the flexibility about choice of logic comes into play, because now this proof, when we insisted on having the Curry-Howard isomorphism and we have dependent types and our terms and our and proofs are one and the same, now the form of logic we use is completely clamped down by the form of programs we have, right? We've locked them together, so we can't vary them independently. This, I mean, I'm not saying this is like rocket's genius idea. This just like seems like a, I don't know. I'm surprised people. I'm not aware of anybody really saying to do this before, but it seems kind of obvious. Now we basically break the Curry-Howard isomorphism, not because we basically love it for practical use as a programmer, but in the end, for a core foundation, we're saying we don't really need that. It'd be simpler just to have a language of programs and a language for proving things about those programs. So basically, so now the programming language and the proof language are not locked together. You can change them, and so this could very well be a classical proof, and it could be written in some totally different notation. You don't have to worry about kind of like, oh, would this be, what's the most sort of programmer-friendly notation? You could use some. I actually I made some brief attempt at figuring out what's the state of the art in classical higher order logic proof formats. I got some leads from an expert in the field, but didn't have a chance to really follow them yet. But it would definitely be higher order logic, though. I mean, and the good thing is, so say it was simply classical higher order logic with some axioms, with a type for terms, like the top type, and basically just some axiom for beta equivalence. Then you could basically, our core theory could be very, very textbook. It could just be classical higher order logic with a theory of untyped lambda calculus. I mean, that is not right. That doesn't need like a lot of defense. Okay, so that's that part. And let's see. Okay. And now I want to mention this one. Okay, I'm going to try in just a few minutes to squeeze in this one amazing thing that was necessary to make this work. And maybe you may have some questions or comments. And let me try to get through this real quick, and then I'll see what you think or have to say. But so let's look again at like NAT, and in the surface language, let's just say, for sake of simplicity, that we're just working with good old. And I don't care what the order of X and XRX is here. Some people care more, but working with good old church encoded NATs. If not familiar to you, then then this part may be not so easy to follow, but this is, you can easily find resources about this. So NAT, we're going to translate this. So what are we going to translate this into? I said we're going to translate it into a predicate, and I'm going to call it NAT eq. To express that it is some sort of equivalence relation. And so this is a predicate on terms. So it says it takes in two terms, X and Y. And now we want to make a statement about them. And the statement we make is derived completely mechanically from the type we start with. There's no, this is where a compiler can absolutely simply translate the type. And what it translates it to is this. It says for all P, that's a binary relation. So every type quantification above, like here, I'm translating this, I'm going to call it P to suggest a predicate. I could have just called it X. Here I've got this type quantification. I'm going to turn it into this quantification over relations, over binary relations. And now we're going to say, well, for any X such that, any X and Y, yeah, yeesh, such that P holds of X and Y. This is the base case. This whole big block of stuff is corresponding to just that single X there. So any X and Y that are related by this relation, and furthermore, any, now we need to say any,
question?
Oh yeah.
So I don't, it seems like you reused X and Y.
Oops, thank you.
Twice.
Thank you. Yes, you probably saved me a problem.
Okay.
You did definitely save me a problem later. Thank you. You're right. I should not reuse X and Y. Yes. Thank you very much. That helps a lot. I was going to get to the end and have to erase. So let me do that. Fix it now. Thanks. Yeah, definitely. So yeah, I should just pick some other variable names. Like I'll just say A and B. Thank you very much.
But
Okay.
so those two positions are meant to be related to the lambda x and the lambda y above,
The
or
Well, the
which?
lambda x and the lambda y above, those variables. Yeah, so we're basically trying to represent this statement we're making about x and y. And the statement we're making is that, well, for all binary relations P, and then we're going to have a bunch of conditions, and it's going to then imply something about x and y at the end.
Okay.
So the conditions are, well, for any A and B that P relates, and this is basically a base case, and furthermore, for any F and G such that for all inputs to those guys, so let me try. If P relates this A and B, then P should also relate F of A and G of B. Okay, so this clause here, this is corresponding to the x to x bit. Okay, and it's saying, you know, for any F and G that preserve this relation, whenever you have inputs that are related by P, then the outputs of F and G will also be related by P. Finally, so basically under these two conditions, then P is going to relate x of a F with y of BG. So it's expressing this equivalence. It's saying if you pick some kind of, essentially A and B here are like the interpretations of zero, and F and G are the interpretations of successor. And so if you pick any way you want to interpret, pick one way you want to interpret zero and successor, and pick a different way, and as long as you have some relation that spans these two ways, that holds of this sort of A and B, the sort of base case, and is preserved by F, then it's going to hold of XAF and YBG, sort of like the interpretation of X the one way and the interpretation of Y the other way. And so this expresses some kind of equivalence of X and Y. And the last thing I want to try to say, which I realize I would not be able to go into details here. So what I sort of was experimenting with this and kind of got led to this early in the summer or even late spring. And only several months later did I realize not that this, if you wanted to use this, so basically what I'm saying is the beauty is once we have this in place, extensional equality in a surface language over NATS would simply be translated to this predicate. So if you want to have this extensional equality that lets you relate things based on their behavior, we're seeing the definitions of all these data types are just their predicates that express that they're equivalent up to that behavior, or they have that equivalent behavior. So that all seems, in other words, that seems really great for giving us an extensional surface language equality. But several months after popping some champagne and such, I was distressed, very distressed, to discover that it's not obviously transitive. And what I said in my little abstract that I was going to focus on today, which I now have approximately -1 minute to focus on, is so I say not obviously transitive because the jury is still out on whether it is or isn't transitive. Chris, in an amazing and very intensely painful looking chunk of Cedille code, managed to show that for the co-inductive stream type, if you sort of follow this whole construction out for the lambda encoding of streams, the equality relation you get is transitive. It was a very clever argument to try to do that, and it was successful, but it looked very hard. And I tried to port it to natural numbers, which have a bit of a different structure, and I gave up. Again, not saying it can't be done. I gave up partly because essentially what you were doing, which was very clever, is when we have one of these proofs, it looks amazing. It looks really similar. Like if you go back to realizability, and this is an important thing to know, I think, and it's important for our sort of Cedil approach. Let's see, where is that? Okay, I guess I didn't write it down for just basic old NAT. If you write it down for NAT, it looks just amazingly like realizability looks just like an induction principle, or very close to induction principle. And so transitivity, you have two proofs of this kind of predicate. They're kind of going to let you do induction, but you must be very crafty about how you, and so basically if you're going to prove that equality between natural, x equals y equals z, does that imply x equals z? If x, y, and z are natural numbers, if you're just doing this, someone says, oh, please do this for me and conquer something, you'd say, that's easy. I just do induction on x, y, and z, and then proceed. And here you can't really do that, but you can try to do something like it, because these predicates are kind of giving you some inductive power, but you have to tinker with them very cleverly. And in particular, you have to be able to do things like say, if I know successor of x equals successor of y, I need to know x equals y. And so I need to know injectivity of the constructors, which I could get if I knew that predecessor of successor of x equals x, but that seems hard to establish at this stage of the development for church encodings. And I tried doing other of our other tricky encodings with this binary thing, and I just collapsed. I couldn't do it. So, but the good news is, and again, this was supposed to be the focus of the talk, there is a surprisingly effective solution that doesn't require the intense ingenuity and trickiness of what Chris pulled off for streams and what I was unable to port to NATs. Surprisingly, there's actually a pretty easy solution using something called quasi-pers. And really sorry, I was hoping to share with you the amazingness of this, but I could just share you I don't know, maybe I'll have to have a part 2 of this to tell you more about that. I do want to stop now, but this is actually really amazing. And this was from a paper by Neil Krishnaswamy and Swami and Derek Dreyer. These are well-known, young programming languages researchers. So anyway, they have a paper about this. I'd have to put the reference somewhere. And they explain how to do basically this, how to get an extensional equality. They don't have quite our magic powers of lambda encoding, so I think we can take this a little further than they did. But you could solve this transitivity problem and work with these predicates. So to conclude, let me come back to what I said the goal is to try to do here. Yeah, so we have a core theory that is, if you say you just took classical hierarchical logic with axioms for beta 8 equality, that's like pretty small. And if you say that's your core theory, you wouldn't have to say, oh, see the appendix for my 15-page argument about why that's all cool. You just say, that's a textbook theory. I don't need to prove anything to you about that. You should just be happy with that. And we could be more flexible about the logic, as you saw, because we're gonna deconstruct Curry-Howard to get just programs and proofs of properties of the programs. We're not looking for these intricately, richly typed things. We're gonna just split them. And then we have this binary parametricity, or this sort of generalization of realizability could give us an extensional equality type, which could be very, very powerful for various applications, including things that several of us care about, like quotient types and things like that. We might be able to get a lot of mileage from this for that. So that's all I have. And I think I don't know, would you guys like to ask or share some thoughts about this? I'll just keep recording. If we decide we don't like to share those, we can cut it or something, but anybody have anything they wanted to ask or raise?
When you had the predicates that you were discussing, are those related to the
Yeah.
Sorry, it's getting late here. Is that I'm
Sorry.
guessing is that why your or the interest in podcasts came for
Yes.
them?
Yes. That's exactly right. Because
And that
these,
explains why there's an episode like, oh, dang it, they're not transitive at
yeah,
the end. Yeah. Okay.
that's right.
Cool.
There's wherever this went. Sorry, where did I stick it? Oh yeah. Yeah, this thing, you're effectively quantifying over logical relations here.
Yeah.
You're saying for all P, and these clauses that follow are basically saying P respects the structure of this signature, zero and successor, in the way that logical relations talks about. What does it mean to respect the structure? Logical relations, this sort of theory of logical relations tells you that, and that's what this is. And so, yes, that's why I got intensely interested in talking and learning more about that.
Is logical relations related to this quasi PER stuff?
The quasi-per thing is, not to go into the details, but just enough to answer that question. Like, basically, what will give you a very quick and easy path to transitivity with seemingly no other painful cost that I can discern, is that right here you say, I'm not just going to quantify over all logical relations P. I'm going to put a condition right here. I'm going to say that P has to be this quasi-per. You add a condition, and what the condition is kind of peculiar. And you look at it like, when I first saw the paper a while back, I thought, what is this? I thought it was really strange, and I actually stopped reading at that point, which was a mistake probably. But coming back to it, it's like,
yeah.
What? Yeah, it's also called zigzag completeness, and it basically just says like certain little piece of graph relationally that you need to draw there's like always going to be a certain edge. Whenever you find a little piece of graph that looks a certain way, there's a magic little edge that's always going to be there. And that existence of that magical edge is exactly what you need to get these proofs to go through. And amazingly, so you basically just add this condition that P it can't just be any old relation. It has to be a little bit well-behaved relation. And you can then prove that all these predicates that you're devising, like this predicate here, is a quasi-per itself. And so that's good. You want that because you're going to want, it's using the same idea of sort of impredicativity. You're going to want to instantiate P with predicates like nat-eq. And so if you've imposed a condition on what P's are allowed to be used here, you better make sure nat-eq satisfies that, and it does.
So the zigzag thing, is that kind of something like the diamond property for a reduction relation?
It's
or maybe weaker or something?
Yeah, it's similarly, it's a very abstract because you're just dealing with relations, right? We have binary predicates. Just think of them as graphs, like just directed graphs. So yeah, similarly to something like the diamond property for an abstract, some kind of abstract reduction relation, the zigzag completeness, it just says, as I was saying, like, instead of saying like, well, every time you go out from a point, then there has to be some way to come in. It's just a different little abstract property. It kind of says, it's so peculiar. Like, it says if you go, okay, it says, anytime you have this picture, you also have to have this edge. Who thought of this? Why the heck this works? Like some kind of more rhyme or reason to it, I couldn't tell you. All I can tell you is this works. I've done it in Cedille, and Ben, our friend at Purdue, did it in Calc, and it's absolutely succeeds. And I could share with you the Cedille code for that if you want to see. It's short and easy. It's not intimidating at all. Chris's stream thing is really, I saw it, I was just kind of, oh my gosh.
Yeah.
How did he come up with this?
Yeah, that one was quite a brain buster, and I wanted to say on that as well. Like I've not really tried to use the same approach to tackle inductive types. And you know, my hunch is that I have some doubts about how it would work out, just because for the streams, the parametricity property of the existential encoding gives you the ability at the right moment to choose the crucial invariant that you want to preserve as you're sort of like unraveling these three streams involved in the transitivity. So you just precisely have what you want within the third one. And it seems like that it's the parametricity property of the existential that's giving it to you. And I haven't got my brain around how that would work for the inductive type.
I was thinking I completely agree with what you just said. Like, this polymorphism is kind of gives you some special flexibility in the middle of your argument to set things up right. But I was thinking of it this way. You would want transitivity to hold just for say you have just a function type, A or B. It's not a co-inductive type. It's not an inductive type. You just got some function type. And you would want to know transitivity for like this same kind of, parametricity inspired equality of functions. You would want that to be transitive. And if you take a few steps of that, you have no polymorphism to try to insert clever predicates at. You're just, I got stuck just almost in 2 seconds of trying that.
Mm-hmm.
That made me think, this probably isn't going to work. Okay, well, our morning people are looking increasingly tired, so let's stop. Thanks for the late night chat, and I'll be in touch with you guys to figure out who might like to go whenever it is next in a couple of weeks. I think I've got it slated for. And I think I talked to Tony tomorrow night. Is that right?
Yep.
Cool. Okay, I should have stopped recording here sometime if I can figure that out. Stop.